Hi everyone, welcome to this session. I'm pleased to introduce Rashmina Menon and Jatinder. Rashmina Menon is a senior data engineer with GumGum, passionate about data and distributed systems. She holds masters from USC in computer science, specializing in data science. Rashmina started her career as a software engineer at Microsoft and has been working on data engineering, data science for the last 10 years. Jatinder, a data engineering manager at GumGum, is enthusiastic about building scalable distributed computing applications and business-driven data products. They will be presenting a talk titled Time Series Forecasting at Scale. Please join me in welcoming Rashmina and Jatinder.
All right, we're good. Thanks everybody for coming in. I am Jatinder. This is Rashmina. We both work at GumGum. We are enthusiastic about building distributed applications, data processing applications. Today we're going to talk about time series forecasting at scale. All right, let's jump right into it. So first, let me introduce GumGum. So GumGum is an AI company. We have two divisions. The first is advertising. In advertising, we utilize our AI technology, which includes computer vision and NLP, to detect unsafe text and images and provide a brand-safe environments to deliver ads in a brand-safe and a contextually targeted world. In sports, we help our marketers and right media holders capture full media value of their brand sponsorship, which could be brand logos, brand placements across broadcast TV, social media, and streaming. All right, so who we are. So we have about 280 plus employees. Our main headquarters is in Santa Monica. We have 14 offices over 4 continents. We work with 70% of Fortune 100 companies. We have 65 plus engineers and still growing. So let's jump into data tech stack at GumGum. So our engineers process over 100 plus billion events every day, and they perform data exploration, data transformations, and data analytics at scale, and provide analytical reports to the business. So some of the data processing system that we use is Kafka, Spark, and Druid. Some of the cloud data stack, all our pipelines, ETLs and data science pipelines are on Databricks. We use Redshift as a data store. We have a lot of data also as well in raw form in S3, and we use Athena for ad hoc queries as well. On the data visualization side, we extensively use Looker, and we recently started using Superset. We are kind of a big fan of Apache Superset. All right, so some of the key highlights. We have 5 engineers currently in the data team. We have over 50 plus data pipelines on both AWS and Databricks. We process roughly 80 terabytes of data on a daily basis, raw data. We have over 40 plus billion real-time events that we process and provide our business insights into business KPIs and stuff. And we process over 20 plus billion data points to predict time series forecasting. All right. So the agenda for today is going to be, we'll kick off with just an intro on programmatic inventory forecast, architecture. We'll talk about the data sampling approach that we took. We'll talk about the forecasting model, which Rashmina will take over, and she'll talk about the accuracy as well, and then next steps. All right, so let's jump in. So programmatic inventory forecast. So before we go into the forecasting inventory, what is the advertising inventory? Or it's potentially a real estate where we can serve an ad on a page, right? So it can exist in different forms. We could serve that in different platforms as well, like mobile and desktop. And so programmatic advertising ecosystem. So it's a technology ecosystem where GumGum is like an ad exchange. So we will automatically automate buying and selling of targeted ads, online advertisements in real time. So if we look on one side of the spectrum, we have publishers. These are content websites. These are some of the big publishers that we work with. On the other side of the spectrum, we have advertisers. These are some of the big brands that we work with, and they're looking for cost-effective ways to place media buys. All right, so they integrate with DSPs. These are demand-side partners. These are some of the big DSPs that we work with. They will work on the behalf of advertisers and will bid on the inventory. And on the ad exchange side, so all the DSPs will connect to ad exchanges. So GumGum is one of the ad exchange where the auction will actually happen, where pretty much during the auction in real time, we will decide which ad to display on which publisher. So the publishers will make their inventory available, and then depending on the auction, who wins the auction, we will display a specific ad from a specific DSP and a brand to a specific publisher. So that's kind of like the chain for programmatic advertising. All right. So why inventory forecast? The reason is when our sellers set up new campaigns, every ad campaign will have a certain type of targeting restrictions. So they would like to know if GumGum's publisher network or inventory can fulfill that campaign, right? So that's the main reason for us to forecast for future days, like next 30, 60 days, depending on the previous days that we have served the inventory. So here are some scenarios. So let's say we're setting a new campaign and they want to forecast inventory available in US, in only Los Angeles and San Diego, only on premium websites for next 30 days for a specific bidder, which is a DSP for a specific ad product, right? So that's one of the scenarios where we will forecast. Another scenario could be inventory available in US and Canada, so it's multiple countries, and also spanning only for sports and entertainment vertical for males age group of 25-40. So that's another reason for them to forecast, depending on all these restrictions set up by a campaign. So for us to set up these campaigns for success, we have to understand what the forecasted inventory is. So let's talk about the scale. So as I mentioned, to set up the campaigns, we have to figure out how much inventory can be served per campaign restriction. So currently we have roughly 30 billion plus programmatic inventory per day. So every day we have this many requests. And they amount to about 25 terabytes of compressed data in S3, in raw format. And our SLA to business is to be able to forecast within less than 30 seconds we're given this information, right? So let's talk about the architecture. So starting from S3, all our raw data is sitting in S3 for all the programmatic inventory. It's a nested ADVERT format. So the first thing we do is we have a daily pipeline. It runs in Spark, where we pretty much push through 25 plus terabytes of data every day to a data transform module, which will just clean and prep the data and also flatten the nested ADVERT object and apply some business logic as well. Once the data gets transformed, it gets fed into data sampling module, which we will touch a little bit later on details of what sampling algorithm we use. Sampling module, which will take the data, transform data, prepare the samples. The next step will be enrichment module, which will enrich the data, all the inventory with additional data from our metadata database, which is Dynamo and MySQL. All right, so once that's done, this is a daily job. It will process 25 terabytes of data on input. Output will be 1.5 gigs of data in Delta format, which we will store in Delta Lake. Rashmina will go in detail some of the performance optimization we noticed with Delta Lake and using Delta format. All right, so now let's say a user is ready to forecast. What's going to happen is they're going to hit our internal dashboard, and the dashboard will hit a Databricks API. That API will execute a Databricks job, which is going to be searching the samples. So depending on criteria or targeting rules that are set by a campaign, we will search through similar samples for that category, for that targeting rules, right? So we will search the samples, which will search for past 365 days, since we want to capture all kinds of trends in our traffic. It will search for the last 365 days. Then it will execute a forecasting model, which is an R model in Spark. And once that's done, once the processing is done in Spark, we'll have our forecast. And end-to-end, all this life cycle takes like less than 30 seconds response time to get the real-time forecast. The daily pipeline is running on a daily schedule, and the real-time can happen anytime, and they will get most recent data based on that forecast. All right, so let's talk about data sampling. So why we sample? As I mentioned, it's too much data, and it will be a waste of resources for us to process 25 terabytes of data per day for 365 days. And also, we want to achieve less than 30 seconds response time for forecasting. So let's take an example. So let's say we have a query. This is just like a forecasting query. Somebody wants to forecast inventory. If we don't do sampling, they will go to the base data, raw data, and then get the exact result. So instead, in sampling, what we end up doing is the query goes to sample data, which is derived from the base data, and we use an estimator. This is called like a scalar factor. So once we have the sample and the estimator, we can actually relate the results back to the original data set, right? And then we get approximate results, which is totally perfectly fine for us to forecast depending on the amount of data that we have, right? And which approximate result should be relatable as well. And we will measure accuracy for sample and approximate result. We measure accuracy in our separate daily pipelines, which will measure the accuracy as well. So that's the sampling. Let's talk about types of sampling. So the first pretty standard sampling is uniform sampling. It's just like a random sampling where every item will have an equal probability of getting picked. But in our use case, since we have inventory, there could be inventory from like a certain, like one user can have 1 million inventory, right? So there could be scenarios where we have a lot of users with recurring inventories, or they're viewing like a slideshow, so they will have a lot of pages visited by that same user, right? So this sampling doesn't perform that well in that use case, so frequency cap. So that's one of the campaigns, like a brand doesn't want to show same ad to the same user like 10,000 times, right? They want to cap it. So they want to cap it, let's say 3 ads per user for 1 day, right? So things like those don't perform well with uniform sampling. So the solution that we ended up picking was distinct item sampling. So this will sample uniform for up to like distinct items to support frequency capping. So this distinct item will be distinct number of users, which is just user IP that we use in inventory, so distinct number of user IPs. And then we'll uniformly sample. And so the sampling algorithm we ended up using was augmented min hash. So this will pick up to m distinct items and perform sample for those m distinct items. All right, so let's talk about the flow for daily sampling that we do. So this amine sampling it is parallelized every hour, and separate hours are combined to get a full day of sample view, right? So how does it look? So we will create samples in parallel every hour. So the yellow boxes are just the raw inventory. The red one is the actual sampled inventory. So for every hour, we will run this min hash algorithm, which will create samples for every single hour in parallel in Spark with up to m distinct hash values. And then once all the samples are done, we will combine those. We'll group by and create like a pre-daily sample. Once that's done, we will generate like daily sample and save them. During this also process, we will also calculate the multiplier, the scale factor. So we can actually, once we get the actual results, we can scale up the sample results and get approximate results. So all this is done in that daily pipeline, and all this is parallelized and distributed in Spark. Now let's talk about search and forecast, which Rashmina will take over.
I have this. Thanks, Jatinder. So I'm going to talk about the search and forecast application. Let's rewind a little bit to the architecture which Jatinder spoke about. So consider a user who is using the dashboard to enter a forecasting query. So as Jatinder mentioned, there is a thin API layer which connects dashboard to the backend. So it exposes an endpoint whose basic functionality is to invoke a Spark job, get the results back, and give it to the user. It got skipped. So sorry for the inconvenience. So basically, the Spark job is what we call the search and forecast application. Now, the search and forecast application, as the name suggests, has 2 components to it. One is the search application and the forecasting application. This is completely hosted on Databricks. So what the API does is basically it invokes jobs API to start the Spark job, get the results back, and send it back to the user. Let's zoom into search application. The functionality of the search application is to read past 365 days of data along with the user inputs and build the time series. So it reads the sample data for 365 days along with the sample multiplier. It has a user input which it gets from the API. And finally, the objective is to build the time series where the number of impressions per day is sampled number of impressions times the multiplier. Where does it read the data from? So if it has to read the data from S3 for every single dashboard request it receives, this is going to incur latency. We won't be able to stick to our SLA of 30 seconds forecasting response time. So the data has to be cached somewhere. So let's see what are the choices we have. To cache or not to cache. Obviously, no caching is not a choice for us because of the reason I mentioned. So the next option for us is to cache the data in memory for Spark. This obviously is lightning fast, but for the scale at which we operate, this is not an option because we'll need a humongous cluster, which is going to be extremely expensive. We'll also need a daily refresh of the cache. As Jatinder mentioned, we have daily jobs that populate the sample data in S3 every single day. So the cache also has to be recreated every single day. So this is going to cause some latency, and also we'll have a downtime. So we want to avoid this as much as possible. So the next choice which we have instead of in-memory caching is disk caching. This works pretty well because disk is obviously cheaper than memory. We can attach as many EBS volumes as we want to the cluster. This also gives us an opportunity to utilize the memory for compute, which is quite nice. I'll come to the point why it's not very efficient, but it also requires a daily refresh like the in-memory caching. Coming to efficiency, when we tried disk caching, we found that we were using 35 C4-2X large nodes for the entire cluster, and it has to be up and running 24/7 to support the forecasting request from the user. The question is, can we do better than this? Can we reduce the cluster size? Can we make the reads faster? The answer is yes, and the answer is Delta Lake with Delta caching. So how many here actually worked on Delta Lake or Delta caching? Not many. This is kind of new because it got open sourced in the last Spark Summit. But this Delta Lake was initially called Databricks Delta, and it has been there for a couple of years, but it got open sourced in the last Spark Summit. The basic idea is this: basically, your streaming apps or the batch apps can write to a Delta Lake. It is backed up by whichever cloud storage you are using, S3 in our case. And the analytics and machine learning apps can read from Delta Lake without having to worry if the asset properties are maintained. Delta Lake also has other cool features like time travel, versioning, efficient partition pruning, and so on. But this is considered an alternative for disk caching, especially if you want to read data for basically inputs. Writing into Delta Lake is very straightforward. Generally, if you're writing a data frame to S3, you specify the format with Parquet or JSON or CSV or whatever. You just use Delta as the format, and you're done. Now that we have enabled Delta Lake, let's see how do we cache the data onto the cluster. So Delta caching is not just available for Delta, it is available for Parquet as well. So even if you're using Parquet format, this is something that could be tried. Delta caching supports accelerated data rates by creating copies of remote files in nodes local storage. So this is the files, the data is stored in an intermediary format, which is much more efficient to read. And this is lightning fast when compared to disk caching. According to documentation, this is at times 4 times faster than disk caching. How do you enable Delta cache? Basically, you need the cluster on Databricks for this, and you have to use i3x large instance type. This is the one which is recommended, but if you're using some other instance type, you can always set certain parameters to enable Delta caching. Once you enable Delta caching and you start reading from Delta Lake, you can see under the storage tab in the Spark UI, a lot of new metrics. You can see how much data is cached per instance, how much data is read from external file systems, which is S3 in our case. You can also see how much data is read repeatedly. So all these user patterns, all these patterns can kind of be used to tune your queries at a later point in time because you kind of know the usage patterns better. Let's see some of the operations that you do in Delta Lake and Delta Table. So if you want to access the Delta Lake, if you don't want to use the complete Delta path, you can always alias it using the create table statement. Here in this create table sample statement, I have created an alias for the long S3 path which follows. Now, once the Delta Lake is enabled, you can cache the data onto the cluster using cache command followed by the select statement. You typically don't need to explicitly cache the data onto the cluster because whenever you read the data from Delta Lake, it is lazily evaluated. So if there is an instance type which supports Delta caching and you make a request to read from Delta Lake, the data will be automatically cached onto the cluster. But here we are doing eager loading. We want to avoid the warm-up time as much as possible. If you want to refresh the cached entries, you can use refresh table statement. This is, again, lazily evaluated. So let's talk about some of the maintenance operations that you do with Delta Lake. If you run optimize command on the Delta Lake, it will compact the files that are stored in Delta Lake to 1 GB size. If you're working on Spark, you know how important it is to have the right file size for distributed processing. So this command comes really handy. If you want to delete the already compacted files, you can run vacuum statement. You can also run analyze table statement if you want to collect statistics about the table, which the query planner will later use for efficient query processing. If you've worked on a Redshift, you will know that vacuum and analyze are typically some statements that you run there as well. And how frequent you want to schedule it depends on the use case. We typically run all these statements once a day. We have scheduled it once a day. So coming back to caching, the answer for us was Delta Lake with Delta caching. Since it's disk caching, we have the entire memory available for compute, which works great. This was the least expensive option for us because remember with disk caching, we used to have 35 C42X nodes. And with Delta Lake and Delta caching, we could reduce to 25 I3X large nodes, which kind of works great. It's also efficient. Generally, you don't have to recreate the cluster every single time. But in case the data is not available on Delta cache, the warm-up queries can take longer time. So that's the only flip side. So coming back to search application, the data resides in S3 in Delta format. We cache the data from S3 onto the cluster using Delta cache, and the search application, which is written in Spark, reads from the Delta cache. Let's go back to search application once again to see in detail what are the operations that are getting done. So the first thing to do is to filter the data from Delta cache. So based on the partition keys, it does first level of filtering. Our partition keys are product, bidder, and date. So it filters the sample data with these filters. The second step is to further filter the data based on user inputs like country, browser type, third-party segments, page categories, everything that potentially can the user use as targeting rules. And we kind of have like 50 inclusion, exclusion steps here. The final step is to aggregate the data to build the time series data. So we have the impressions per day. As Jatinder mentioned, if there is a frequency cap filter set, which says what's the maximum number of impressions that we should get from a user for any particular day, we'll use that frequency cap filter. Otherwise, we just aggregate the data to build the time series. And finally, we multiply the data with multiplier data to get the projected number of impressions. So that's all about search application. Let's go to the second part of the search and forecast application, which is the forecasting application. It takes the output from search application as the input, which is basically the time series data, and gets the resulting time series data, which is the forecast data. So as the name obviously suggests, the intention here is to forecast the trend or inventory impressions for the next n number of days based on the search data. So the model which we use for forecasting is something that we have used at GumGum for various other time series applications as well. So we use AutoArima, written in R, along with sinusoids. AutoArima is a very common forecasting method in time series forecasting. We use auto feature so that we don't have to explicitly compute the parameters. For anyone who has worked on an ad tech business, they know that trends are varying across different quarters. For example, Q4 or the last quarter of the year is typically when we have the most business when compared to Q1. So we capture those trends in terms of weekly trends and quarterly trends through sinusoids. So suppose this is the time series that the search application outputs. We definitely smooth it. We get the quarterly trends through sinusoids, and then we build the weekly trends through sinusoids. We combine quarterly trends, weekly trends, along with Arima to get the forecast. So we have found that this has been really working for us for this particular application. And how do we know it's working well? We measure the forecasting accuracy. The metric which we use is mean absolute percentage error. Basically, we compute the deviation between actual and forecast with respect to actual. A here stands for actual, F here stands for forecast, and we compute the mean for n observations. And with this model, our error has been less than 5% consistently, which is great. With that, we open to Q&A. Also, we have openings in engineering roles at GumGum, so if anyone is interested, please do apply.
Thank you very much for the nice talk, and this is the certificate of appreciation.
Thank you.
And thank you for listening.
Thank you.
Questions?
Hey guys, just have a question on the seasonality. Are there other seasonalities that you have found within your business that you mentioned quarterly and weekly? Are there other seasonalities you think that could affect your forecasting model?
Yes, the answer is yes. For example, we have a lot of business during Thanksgiving, Christmas, and so on. But currently, we are not using the seasonality as a measure because auto-RMA is basically for trends, not so much for the seasonality. But we are planning to evaluate models like profit as how it would behave for seasonality trend as well.
And for that metric that you had, sorry for hijacking the second question, but what's your end value? How many samples are you testing a 5% error on?
So this is generally for 30. The forecast is for 30 days.
Okay.
Yeah.
So it's over a 30-day period?
Yes.
Okay, thank you.
No problem.
Hi there. Thank you, first of all, for presenting this for us. I was wondering, is there a reason why you guys used auto-RMA specifically as a model versus other models for prediction?
The thing is that we have been using auto-RMA for different time series forecasting application. It is kind of like something that we have been using for some time. So that's why we thought we'll test how this would work for our current application, and it kind of worked well as well.
I see. So, I mean, usually when I run projects like this, and I use different algorithms, and then I choose the one that works the best based on my data. And as you know, data changes daily, right? So what works today might not work tomorrow.
Right.
So, I mean, using auto-RMA because it works in the past, using it again and again does not really answer the question, right? So is there a specific reason why it performs better than others, or like that you guys by default go for that, or?
So one reason is that we don't store the model, so user can enter whichever input they are interested in from the dashboard, right? So we are building the model right then, and we are getting the forecast result. So what fits for a time series 1 may not fit well for time series 2. So auto-RMA kind of works well because we don't have to specify the parameter, it will find its own parameters for scenario 1 and 2.
That makes sense.
Yeah.
Thank you.
No problem.
So my question is, when you run the forecasting models in R, are you using Databricks, facilities to get it distributed onto the nodes?
No, we run it on the master node because the data is like really small for 365 days for the forecasting application, right? So we just run it on the master node.
Okay, thank you.
Hi, thank you so much for the presentation. And the follow-up question to the one he asked about the auto-RMA. I have read some research where it shows that extreme gradient boosting has been one of a valuable algorithm used for demand forecasting. So I wanted to know what is the difference between the two scenarios you mentioned, which works well with auto-RMA? Like, is it in the difference of the data that is causing auto-RMA to work well, or is there?
Typically, if you use auto-RMA, you don't have to specify the parameters because our model will find it automatically, right? So that's one of the advantages for auto-RMA. So we don't, the time series keeps changing from one user request to another, and it can be really varying depending on what is the targeting rule the user enters. So that's the key reason why we use auto-RMA in this case.
And just a follow-up question. Has there been any measures taken to reduce the error, like the error measure less than whatever it is right now?
It has not been a key request from the business or even for the engineering, but we are planning to evaluate profit, as I mentioned, and probably LSTM or something like that, yeah.
Thank you so much.
No problem.
Hi. Sorry about that. Thanks for a great talk, first of all. I have a question about your overall architecture. So you have sort of fairly complex pipelines for reducing data. For example, you have a big daily run. And a lot of that's driven by your data size, as I understand that, the 25 terabytes that you're ingesting. Have you looked at at technologies that might allow you to just process straight off that data as opposed to having to do a bunch of downsampling? So for example, like column storage, compression, things like that. And if those existed, how might that change your design?
You want to take that? Yes, I don't know.
There is only one mic. Yeah, 'cause that was the other one. All right. Yeah, so I think even if we are currently using columnar file format, Parquet on S3, even with the columnar file format, if we forecast on a full data set, full inventory, our inventory is growing like exponentially, right? We can't consistently keep up the compute cost. So there's always some trade-off that we have to do. So in our use case, it was much easier to maintain like a daily sampling pipeline in order to reduce the data set and also like measure the accuracy of those samples over time so we can accurate the samples and then we get good forecasting results with a minimal cost for the business as well. Yeah.
Okay, and just a follow-on question to make sure I understood. Do you hold over the 365 days, do you hold the raw data or is it just samples?
Samples, just the samples, yeah.
All right, thank you.
Yep, you got it.
Sorry, it's me again. I was just wondering, talking of the infrastructure of it, by the way, it's awesome. And I was just wondering, I'm assuming this data is being streamed, right? There is no downtime or like minimal downtime. Like I think if I remember, it was 30 seconds, right? So what allows you to stream the data? And because I mean, as you know, like when you run the models, they take a long time to run. What allows you to, I'm guessing the samples are small, but still it's 60 terabytes. So you still have to have what, like 10% sample? So you still will have to kind of like have some processing time. How do you guys work with that?
So as I mentioned in this presentation, one level of filtering is done using efficient partition keys. So we have predefined user patterns that the user will query upon. So bidder and product are the major partition keys. So that will perhaps reduce the data to 50% or even lesser. So that's one level of filtering. Second level of filtering happens through dataset APIs. So we use dataset APIs all throughout, and it has been working quite well.
So what is the dataset API?
So dataset is basically it's written in. I mean, it's basically in Spark. So if there are different levels of data sets that you can have in Spark. It can be data RDDs, data frame data set. So among these, data set is the most efficient.
Okay. So you could just take it directly from the API and process it using partitions?
So dataset allows you to have a strongly typed data. So basically, if you use dataset APIs, the most recent version of it, it enables you to do the filtering and transformations in a much efficient way.
But it still takes time, right? Even if you partition it and everything, you still are not live.
No, it doesn't take more than 30 seconds.
Really?
Yes.
Oh, that's pretty impressive. Thank you.
Yeah, it's also because you're not reading the data from S3 every single time, right? So everything is backed up in Delta cache, and that's where it becomes way more efficient. So as I mentioned, it's like 4 times faster than disk caching in most of the scenarios.
Any other questions? Okay, thank you.
Thank you.